Hello, I'm Kyungwoo, working for Meta. 2 years ago, I introduced global function merger here at EuroLLVM 2023. I'm very excited to share that all these features are fully upstream. That are available in Clang 20. And also we take back into integration into our production in a scalable way using the distributed DNLTO. Plus the Alex, the next speaker, who is going to, who actually has taken a step further to address one of the most challenging symbolication issue for the merging functions. So our mobile apps are getting bigger and bigger because we keep adding new features. As you know, large and slow apps make an impact user experience and user retention, resulting in our revenue. So it's critical to make mobile apps smaller and faster. If you look at this graph, in particular the blue line, where baseline optimization is just applied, the app size growth has quickly increased just in a year, which is over 20%. However, if you see the green line on the bottom of the graph, the growth rate is much lower because of our aggressive size optimization, like a function outlining or function merging, which I'm going to cover mostly in this talk. So here is agenda I'm going to cover. Basically, I'm going to introduce global function merger, which leverages linkers identical code folding called ICF. Next, the next speaker, Alex, will talk about new ICF capability with the thongs. And then he's going to talk about some challenges that we face when we about symbolication of stack traces. And also he's going to talk about how to ensure sound stack traces for the merge function that are relevant for the developers. So traditional function merger typically compares entire IR to see if they are identical. In fact, the linkers ICF does a similar job. So when we enable, so the importance of the traditional function merger is minimal when we enable ICF together, which is typical setting in production. There is another function merger in the Swift repo, which is able to not only identical, but also similar functions through parameterizing differences among the functions. Let me give you a more concrete example with the two functions. They look very similar, except the core constant target, which are F1 and F2. If you merge them, we can come up with a single merge function with extra parameter x2. While these original functions foo and goo become thunks, while providing extra parameters f and f2 through parameters. The downside of these traditional function merger is that they are only able to merge function within a single module. Unless you combine everything into single module using LTO, then you are not able to merge functions across modules. In contrast, the global function merger is able to do that even in a separate compilation environment like a DNLTO. It actually uses the Cogen data framework that has been initially implemented for global function outliner. Basically, at the high level, it has two steps. The first one acts as a writer generating Cogen data summary that can be merged at link time. The other one acts as a reader. It consumes the Cogen data produced from previous step to optimistically create merging functions. As you know, that DNLTO backend compilation runs in parallel and independently. So there is no single orchestration. So not only that, there's a chance of staleness of Cogen data summary that we produce. So our transformation is based on this summary data. We cannot just merge in place which can lead to miscompilation. Instead, we actually merge the functions at link time. The way we do transformation during compilation is just canonicalization of the function into certain merge function form. Let me give you a more concrete example. Let's say in the first step of the TO, we can start with the original functions with two modules like this. They look very similar, similar to the case I've shown earlier. We first analyze each function into stable function form, which are independent of intermediate representation IR. As you can see, we come up with the hash value, which is based on content of functions, and also just string name, and then locations of constants that we ignore, basically indexed to the instruction and operand, and then the associate with constant hash value that we ignore. When you combine a link time, we can combine into single summary that are grouped by same hash value. And also we compute the parameter that are minimal set of the locations that are different among the stable functions with the same stable hash value. In the second pass, we start with the same module IR. Now we compare against the summary, and then we can optimistically create merge functions like this. As I said, these module compilation run in parallel independently. So we have to make sure the merge function have unique function name. At the end of linking, if they turn out to be identical, then we can combine into single function through ICF capability. So this is graph the LLD binary size improvement when we apply global outline and merger together with the thin LTO versus LTO. These are compiled under OZ, which is minimal size optimizations. So as you see, the global outliner flag is the same as local outliner flag, machine outliner, enable machine outliner, which is actually on by default for under OZ targeting Arch64 Arch, ARM64 Arch. I also introduced merge flag, which is enable global merge function. These flags, depending on cogent data used or cogent data generate, depending on these two modes, it could operate as local, which is default. When it consumes the cogent data based on the previous summary data, it operates as global mode. Of course, you can run in back-to-back using single flag, but this is the only case for local thin LTO. If you are about to using this technique for no LTO or distributed thin LTO, you have to use two explicit steps, which is gen and use. We have been tracking the relative edge size over the past 3 weeks while updating the cogent data weekly. If you see the red, which is only outliner enabled case, this relative size of overhead is pretty low, within only 0.2%, which is pretty impressive given the fact we have hundreds of thousands commit in our source repo. I think this happens because outliner exploits very short machine instruction sequences that tend to be very repetitive and stable. So it's very insensitive to any source changes. However, if you see the blue line where merge is enabled on top of the outliner, the size overhead becomes more noticeable, up to 0.7%. But still, it's not bad, less than 1%. Merger summary is basically more sensitive to source change because summary for merge is entire function rather than small outline sequence. So that's why it happens. So depending on the build resources you are allowed to use and the size overhead that you are willing to accept, you can adjust these refresh rate accordingly. Now I'm going to hand it over to the next speaker, Alex.
Hello, everyone. I'm Alex, also working at Meta. And the previous optimization logic was implemented in the compiler. Now we're going to see how we improved function merging in the linker. So the linker is able to perform identical code folding, known as ICF, where it can only merge binary identical functions. Here we have an example as an example source code, two functions A and B, and a function main, which takes the address of A and B, compares them, and returns the result. So we always want to return false here. The address of A and B should never be equal because they're different functions. As we can see in the object file, these end up as A and B separate functions, but identical. And then the function main takes the address of A, takes the address of B, compares them, and returns false. However, when linking with ICF equals all, which means that all functions that are identical will be merged, we see that we end up with only function A being kept, and then function B being merged into it, and all occurrences of B being replaced with A. So that ends up with main taking the address of A twice, comparing it to itself, and returning true. So this is a functional change that we got from enabling ICF that causes bugs and crashes in applications. So how can we still perform ICF while maintaining program correctness? We introduce a new ICF mode called save thunks, where we keep only, when enabled, we keep only one full body of the function, and then all of the identical functions, we replace them with thunks, which consist of a single branch to the full body. So we can see here that in main, we take the address of A, we take the address of the branch of the thunk of B, and then compare them and correctly return false. So we maintain correct program behavior. So for the ICF, when enabling this for real-world applications, we've observed about 0.45% size savings when compared to regular safe ICF. This is upstream for the LLD Mako ARM64 linker, and it takes one flag to enable. Okay, now all of this function merging leads to issues with debug information, as we'll see. So taking a different examples, function A and B are functionally identical, but they have different source code. And then the function main calls B and then calls A and returns. We can see that in the object file, we end up with two binary identical functions, but different debug informations for them. And the function main, we just call B and then call A and return. When linking with ICF equals all, we see that we only keep one full body of the function. We don't care about addresses here because addresses are not used, so this is correct program behavior. And then in the function main, we branch twice to the merge function, one corresponding to a branch to A and the other one corresponding to a branch to B in the original source code. And we can see that in the symbol for the binary, we only keep the symbol for A, and same in the DSYM debug information, we only keep the debug information for A. So at this point, all information of B has been completely stripped out. It's actually not possible to tell at this point that B existed at any point. So this function merging can lead to symbolication issues, as we'll see. So we take the previous example again, and then we see how a crash in A would look like. So a crash in A would look like a frame in main and then the top frame in A, as you would expect, so this is correct. However, a crash in B would also look like a frame in main and a frame in A because they have been merged together and we've lost all debug information for B. So this can be very confusing for real-world applications where you have tens of thousands, hundreds of thousands of functions arbitrarily merged together relative to the logical source code, and developers end up with very confusing call stacks where apparently completely unrelated functions are being called. This generally ends up with them thinking it's some sort of memory corruption issues and debugging for hours or days and figuring out that it's because of merged functions. So in order to symbolicate this, we see that we'll need more data to perform correct symbolication in this merged function scenario. So what we do here is we keep all of the symbols for all of the merged functions, even if they point to the same address in the binary. So here we also keep the symbol for B. Then in the debug information, this debug information, we keep all the debug information for all of the merged functions, and we keep all of the call sites in the binary. So wherever a call is made, we keep the address that it's made from and the target where it branches to. And similarly, in the GSYM debug information, which is just an indexed faster version of the DSYM debug information, we keep the debug information for the merge functions and all of the call sites. Now, how can we use this information to perform correct symbolication using the GSYM debug format? We take here the previous example in a typical production deployment where we have the completely stripped binary and the GSYM debug information for that binary with additional data. And now we see how we can resolve a stack in A. So from the client, we get the raw frame addresses within the binary. And in order to take this approach, we symbolicate from bottom to top rather than, as usual, from top to bottom. So we take the first address, 0x10. We look that up in the GSYM file. We see that that corresponds to the main function, but it also corresponds to a call site to A. We'll use this as a hint later on. So we can look, the lookup returns main plus call site A. So we can correctly symbolicate the first frame as belonging to main. And then when looking up the next function, we retain the filter from the call site as we apply the filter A for the next lookup. So then when we go into the GSYM and look up the address 0x04, we see that this corresponds to two functions, A and B. And then we can by applying the filter, we can correctly narrow this down to A being the functions, the debug information associated with the correct functions that we're looking for. So we can correctly resolve the full call stack as a frame in main and a frame in A. Now for a call stack for B, a crash call stack for B, we again get the raw addresses from the client, and we see that the only difference here is the address for the first frame. So when looking that up in the GSYM file, we see that again it corresponds to main, but this time it corresponds to a call site for B. So the lookup returns main plus call site in B, and then we correctly resolve the first frame as pointing to main. And for the second frame, we apply the context filter B. So then when you go to look up in the GSYM binary the address for the top frame, we see that again it's A and B, but applying the context filter B, we can correctly narrow this down to needing the debug information for B. So we end up with the correct call stack here with the bottom frame being main and the second frame being B. So this is how we can use the additional debug information to provide correct call stacks in our applications where we maximize code size by enabling as much function merging as possible. So this implementation is currently upstream. It's currently upstream and it supports symbolication via GSYM for Mako. But it is possible to extend debuggers and other symbolication pipelines with this approach. And to enable this, we needed to modify and we need to pass flags to Clang, to LLD, the linker, and we need a recent version of DSYM-util. And then for the symbolication via GSYM, we need to provide additional flags and also to change the way we call LLVM GSYM-util to perform the resolution, the symbolication of the call stack from bottom up. Yep, and yeah, that's our approach for correctly symbolicating debug information. Okay, now both of us can take questions. Oh, wait.
Hey, interesting work. Does this work for indirect function calls, like function pointers or virtual functions?
So right now, upstream, we only have enabled support for direct function calls. We do plan to add support for indirect function calls like virtual functions and Objective-C selectors. We'll base that on the function name. So the context filter in our case is actually a regular expression. So we can use the function name for virtual functions and the selector name for Objective-C selectors to narrow it down to the correct function. Now for raw pointers that you just arbitrary call. We can potentially narrow it down to like a few functions that we can show to the developer. That's the plan, but it's difficult because that's basically just like user input that translates to a function, so it's not really possible without having some sort of data analysis also integrated into this. Yeah.
And this looks really cool. Are there any plans to extend it, to do work to extend it to the other formats and architectures, or you don't have a need for that?
So we don't have a need for that, yes, unfortunately, but we have designed it to be extensible and usable for other architecture. The GSYM format is actually supported. We use it for symbolicating other architectures, so we might enable that internally and also ship it upstream, but there are no plans right now to do so.